Distinguish between frequency and angular frequency for a body undergoing simple harmonic motion. Frequency f is the number of oscillations per unit time, whereas angular frequency omega is the rate of change of phase angle. Since each complete oscillation moves through a phase angle of 2 pi, the angular frequency equals to 2 pi f. In mathematical form, omega is 2 pi f. A spring that has an unstretched length of 0.65 meter is attached to a fixed point. The mass of 0.0 kg is attached to the spring and gently lowered until equilibrium is reached. The spring has then stretched elastically by a distance of 0.2 meters. Calculate, for the stretching of the spring, the loss in gravitational potential energy of the mass and the elastic potential energy gained by the spring. Now, the loss in gravitational potential energy is given by mge or mgh. This is the length, is 0.4 times 9.81 times minus 0.2 meters. So you get 0.785 joules. So that's a loss. The elastic potential energy gained by the spring, since the mg is ke, so the energy is half k e square. So that will give us half mge. Substituting values, we get a gain of 0.392 joules. Explain why the two answers to B are different. Now, an external upward force is required to support the mass when it is lowered gently downwards towards its equilibrium point. Thus, some gravitational potential energy is lost due to the negative work done by the external force, while the remainder is converted to elastic potential energy that is stored in the spring. Note that the external force is not required if the spring is dropped suddenly. So if the spring is dropped suddenly, it will start to oscillate. So there will be energy stored as spring potential energy as well as kinetic energy. In this case, because the external force, the hand, is lowering the mass gently, there is no kinetic energy. So its work is done against the external force. The load on the spring is now set into simple harmonic motion of amplitude 0.2 meters. Calculate the resultant force on the load at the lowest point of its movement. So F net will be equal to kx minus mg, and substituting all these values, we get the net force as mg. F net is 3.92 newtons. Calculate the angular frequency of the oscillation. By Newton's second law, A is equal to F over m. So for simple harmonic motion, A is minus omega square x. So omega will be equal to A over x, and that will give us F net over mx. So substituting values, we'll get omega as 7 radian per second. Calculate the maximum speed of the mass. The maximum speed of the mass is given by omega x naught, and that is 1.4 meter per second. Figure 6.1 is a table of energies of simple harmonic motion. Complete the table. So at the lowest point, the mass is momentarily at rest, so that means that the kinetic energy is 0. The extension is 0.4 meters, so the elastic potential energy is half kx square or k extension square. So that gives us a value of 1.57 joules. And the total energy will be equal to sum of the three. So that will be 1.57 joules. Now at the equilibrium position, the GPE is mgh. So that is a 0.785 joules. The elastic potential energy, K, given by B2, calculated in B2, will be 0.392. So the KE will be total energy less gravitational potential energy less elastic potential energy. That will give us 0.392. At the highest point, the GPE is 1.57 joules. So that is the height. Therefore, the other two has to be 0 because the total energy is also 1.57 joules. On the axis of figure 6.2 below, sketch 4 graphs to show the shape of the variation with positions of the 4 energies. Label each graph. So the total energy is constant, is 1.57 joules. The GPE is given by mgh, so that is a straight line graph. So that is the gravitational potential energy graph. The elastic potential energy is a half k E square, that is a curve. So it's given by this value, it passed through 0.392 at equilibrium position. It's 1.57 at maximum and 0 at the minimum. At the highest point is 0. The kinetic energy is a half m omega square x naught square minus x square. So there is a curve. Okay, it's a x square graph.